Yes, that. Yeah, so these guys are not, right, these guys are not aromatic the way that they are over there. They have, like, with one of the members of the rings is sp3 hybridized, right? You've got a CH2 connected to two things in the ring. That's not, that breaks the whole thing, it doesn't work. But, oh god, oh no, oh no. That's 1, 2, 3, 4, 5, 6, 7. Yes! It's ugly, but I did it. Alright. So, these guys, well, okay, I guess if they're gonna be like that, then cyclopropene has the correct number of pi electrons to be aromatic, because 4 times 0 plus 2 is 2. Fine, sure. Alright, any even number that's not divisible by 4 is aromatic. Any even number that is divisible by 4 is anti-aromatic, as long as all the rules are followed. Okay, so these guys all have, this guy has 2, so it's not divisible by 4. That one could be aromatic if we fix it, make it follow the rules. This guy has 4, so that guy, if we try to make it follow the rules, could be anti-aromatic, but like, if we try to make it follow the rules, we're already gonna make it less stable, and then anti-aromatic would make it like even more less stable than the less stable that it should be, so we'll see. And then this guy has 6 pi electrons, right? So this guy, if we make it follow the rules, could potentially be aromatic. So what happens is, wait, do they tell us how we do this? Yeah, aromatic, and yeah, if the CH2 group becomes a CH plus group, then the atom would be sp2 hybridized, and the vacant orbital would go into a 2p just because it's next to conjugation, so that it could also hang. And they're not gonna talk about how we do that. Oh, here we go. That's one of the ways to do it. Whatever. If you can deprotonate, oh, that's a. All right. If you can get this to be a CH plus, so I guess not deprotonate. You would take a hydride away, so you need a leaving group that can take the electrons with it. If you can have a leaving group there and get rid of it, so you have a positive ion and you have a positive charge on that carbon, then all of a sudden you've got an empty p orbital. And so when we count the number of pi electrons, they don't change, right? Because a positive charge is just telling us there's less than there should be. In the case of carbon, a positive charge just means a lack, an empty orbital, because it's not supposed to have any lone pairs anyway, so it's not just too many bonds, it's just, somebody stole my electrons and now I have a whole orbital that's just empty, and there you go. I don't know. So that's what that means on a carbon, which means that we've got, all of a sudden, we've got a p orbital on every member of these rings, right? Because this side isn't contributing anything, but it's got the space to hang out and be planar and like let the conjugation roll through it, right? So these guys all of a sudden follow the rest of the rules. In which case, this still has 2 pi electrons, so it becomes aromatic. This guy, we're not going to be able to form, so let's get to that in a second. And this guy would be 6 pi electrons, so it's aromatic. Now this guy, well, okay, we can't make it a positively charged ion, but we've already drawn, we've already drawn 5-membered rings that we decided were aromatic, right? As long as that fifth member of the ring that doesn't have any double bonds to it has a lone pair, then it can be aromatic, right? Because then we've got 6 pi electrons. So what if, instead, for this one, we do negative charge, and then I'll do a little, there. They're in the pi orbital. Now we have 6 pi electrons, right? On this 5-membered ring. So if we make a cyclopentadiene can form an aromatic ion, just it needs to form the anion. So normally we don't really like charges on carbons, right? Like just as a thing that's like, yep, this is just a charged carbon, and we're gonna talk about it as its own whole ass compound or whatever. Like, not generally, but in these cases, we formed aromatic compounds by making an ion, putting a charge on a carbon. And of course, we haven't really put a charge on a carbon. We have put a charge on a ring that's just sort of nice and distributed around the ring, right? So we can actually form these guys. And they're pretty stable, like way more stable than most charged carbon like intermediates that we draw between things. This guy, in this case, we actually might want to talk about a pKa, because these guys, you have to have a leaving group that takes electrons with it, right? But this one, if you just deprotonate this, then that's that. You made it aromatic. And so the pKa of this is, the pKa of the hydrogen that used to be here is 16. So like, as acidic as an alcohol, that's, right? Yeah, alcohols are 16? Yeah, that's pretty acidic. I mean, you know, you'd have to be, when we're talking about like water and like aqueous NaOH, we're gonna have to have, you know, aqueous NaOH, not just like a weak base to have a decent amount of this, but like, also we can get the pH low enough to have a decent amount of this around just with water and sodium hydroxide, right? We don't have to do special organic bases that are extra strong and whatever. So yeah, we can make this guy. And PKEQ, why do we have a PKEQ? Whatever. If you use sodium amide, oh, okay. Wish they had drawn sodium amide for me, because is sodium amide, hold on just a second. That makes it sound to me like, okay, yeah. Sodium amide is, this is not green, NaNH2. So it's nitrogen, kind of this. Like, it's basically a deprotonated amine. Not a deprotonated protonated amine, right? Because if we look up, if we try to find amines on our pKa table, it's gonna show us NH4 plus, and it's gonna show us that going to NH3. And it's gonna give us pK for this. This is, if we start with NH3 and want to go to NH2 minus, right? So this is essentially NH2 minus, sodium amide. If we take that guy, that is a very nice and strong base, and instead of having an equilibrium like this, we can just make all of it the cyclopentadiene anion. Cyclopentadienyl anion, whatever. We can make cyclopentadiene into its nice little negative ion that is aromatic.
So is the fact that they're showing an AOH, is that
They have that shown because they say it right here. When treated with aqueous NaOH, an equilibrium is established and some of it's converted. And they couldn't fit the picture that goes with this on this slide. So instead of taking this and putting it on the slide, next to the picture that it's about, they just sort of put this on its own slide with no explanation because reasons, and then put this that's not referring to that, and then no picture. I don't like it. They make poor decisions sometimes. Many times.
How does the base give the anion?
So let me get rid of all of this garbage. Previously, perhaps useful, but now garbage. If we have we'll call this. All right, let's do this. If we've got this and we go, hey, let's have sodium amide. All right, fine, I guess I'll draw the sodium, but I'm not drawing a bond between it. Sort of, I don't know. You're not wrong if you draw it like this. You're not wrong if you draw a bond between it and sodium. You're not wrong, and you make me slightly less if you just put sodium right next to the nitrogen and don't draw a little bond between there and just don't make it a bond, because then we didn't draw it, and then we're not trying to claim it's ionic covalent. See, words. God. This is something I need to work on before I get an interview somewhere and then have to go teach a practice class. Luckily, I don't think they have you teach a practice class to hire you for visiting professorships. So luckily, they won't see me do this. So if we take this very strong base, hey, nice, these markers work much better when I just keep them here and store them upside down overnight. Then we can deprotonate, so the bonding electrons go onto the carbon, and we get wait, I circled negative charge. A negative charge on there, right? And this guy is only aromatic if we get the negative, the anion, not the cation, right? Because we want 6 pi electrons, not 4 pi electrons. So yeah, yes, yeah, cool. I figured it was one of those things that the second I had something drawn up there, you were like, oh, dang it, okay, yeah.
Yeah.
But I keep going just in case.
So with the cation, would the NP orbital thing work with other compounds that are not cyclopentadiene?
Yes, because when we have this one, remember the triangle and the
Oh yeah, we
yeah,
went over
wonky
that,
ass
sorry.
7-membered ring? Yep. These guys,
Cool.
you can do the same thing, you just have to have a leaving group so it takes the electrons with it. We're not gonna do that example. Okay, nomenclature. With nomenclature, the thing that I want you to know, it would be useful for you guys to have an idea of phenol being benzene with an OH, and aniline being benzene with an NH2, and toluene being benzene with a CH3. Like it would be useful in your daily lives if you do anything tangentially chemistry related at all. It would kind of be useful to know those, just because you'll find no one who uses like the ID pack name for those. So luckily you'll have your phone on you, so you can just, Google it later if somebody uses it and you don't remember. So monosubstituted alkyl benzenes, we call it phenyl. Let's see, why is that a benzyl group and that's phenyl group? Oh, okay, got it. If these guys are like, if you've got a benzene ring as a substituent coming off of something that is, like something else should be your main chain, so you've got something coming off of there. If you've just got a ring coming straight off of there, you can call it phenyl. That's just a little sticking off the side thing. If, like in the middle of a ring, you've got a CH2 and then a benzene, you can call that benzyl, I guess. Didn't know that. But, a lot of times it's part of the, they just keep calling it phenyl. All right, cool. If it's got a bunch of stuff on it, then it just becomes phenyl. If it just sort of has substituents, like tiny little substituents, then we call it something benzene. So like, if we just had, 6 single bonded carbons coming off of here, then we'd call it 1. We probably wouldn't even have to say 1 because with rings you don't have to. So hexyl benzene. Yeah, hexyl. Hexyl benzene, right? Hexane, hexyl benzene. Yeah, I think so. Anyway, who cares? The thing I want you to know is orthometapara. This is going to be useful. So when we just have like functional groups on the benzene, so the name that we would call it, except for, things that have their grandfathered in names, toluene, aniline, benzoic acid, xylene, literally all of the ones that they're showing us here, I guess. When things don't have the special grandfathered in names, we have orthometapara, there we go, for disubstituted benzenes. If we get to trisubstituted, then we don't have special names and you just number them. That's fine, whatever. But for disubstituted benzenes, or at least, not just for disubstituted benzenes, you can use orthometapara to describe the location of one substituent in reference to another substituent, right? So even if there are a bunch of like substituents on here, you can say ortho to the bromine, or meta or para to the chlorine, to the nitro, right? So that's orthometapara. Know these guys, yes.
This is in reference to the carbon they're on, not like the 1,4 thing that we did on the quiz yesterday. That was like, you start at the, like if there's a ketone, you start counting at the oxygen, then get down to the carbon. Like for 1,4.
Oh, yeah, no,
like,
it's not.
that
Don't
weird
start
kind
counting at the oxygen. Yeah,
Okay.
no. Sorry, that's like a, yeah, I know, I hate it. Like 1,4 addition is like but I'm using I guess technically I guess that's why it's called an Michael reaction, because they didn't want to call it 1,4, but
Because on the
Still
previous
is.
slide said para was 1,4, but that wouldn't be 1,4 if it was the other counting system.
yeah, no, this is the, like, yeah. So when we are naming, like, reactions or steps in a reaction, or like a substitution reaction or something like that, or addition, I guess, the numbering system is like wonky and stupid, and you don't have to know that. And then whenever we're doing like half the time when I'm up here and I start going, I'm gonna number members of the ring, so I'm numbering the oxygen too, because this is how I feel and this is what I'm doing, because I don't know. That's just me making up my own rules to keep track of things. This is in the realm of back when you were actually taught naming instead of just being pretending that we're doing naming, when you would find the longest carbon chain, and you'd only ever count carbons, right? When you're doing that, or when you, if you've got a ring, so you're naming like a cyclohexane, and you've got some substituents, then the highest priority substituent is going to be 1, and then you're going to number in the direction that you get lower number for the lesser priority substituent. That's how these numberings go. So basically, you don't even have to know the numbers. You just can know, like, I remember these by shapes. Like, I literally just remember these as like, oh, ortho, meta, para. Like, yeah, good clock. Or like my fake cheerleading up here. Fake that cheerleading up here? I don't know what I'm doing. So yeah, ortho, meta, para. Ortho, right next to each other. Meta, one further away. Para, all the way down here. You will, when we get to chapter 22, learn to associate ortho and para as, when we get to the point of directing groups, and so we have something on there that like, we'll have substituents, electron withdrawing or donating substituents that'll contribute, sort of control, like, where we're going to make substitutions. We can either be meta-directing or ortho-para-directing. So you can't really just para-direct or just ortho-direct. I mean, unless you just use an ortho-para-directing group and then already have a substituent on one of those, I guess. But like, this guy is kind of on its own and these guys are associated. And you'll see that later, but you don't have to know that now. You do need to know ortho, meta, para. Yeah? Cool. These guys, you just number them. And polycyclic aromatic hydrocarbons get all sorts of dumbass names: naphthalene, anthracene, phenanthrene. These are not, I think like all of these are grandfathered in, and I don't even know if there is a way to do IUPAC naming with this. There actually might be, because I think I don't know, ChemDraw can do some, if you have the right ChemDraw that can like just structure to name, which we don't here, you can generate some like truly wild ass names that you're like, there's no way people call it this, and then you can find the compound somewhere else and they like, you know, use, oh, well, this part is kind of called styrene, so they just sort of Frankenstein together a name based on that part so that it wasn't as stupid as the IUPAC name, but I don't even know if you can IUPAC in those. All right, let's start on, it's 9:27. We're not gonna get all the way through phenols, because this is, yeah, too many slides for me to do in 10 minutes. So we could start phenols so that we have a much better chance of getting through, of finishing this chapter quickly and having time to